All right, welcome to lecture 3 of the second chapter of Nature in Code. And this one is entitled Hardy-Weinberg Part 2. Because last lecture we talked about Hardy-Weinberg in a lecture entitled Hardy-Weinberg Part 1. So just to recapture what happened until now, we basically had a population of 100 individuals, and we calculated the genotype frequencies. We counted them to be more precise, and we found 15% were A1A1 genotype. We also found that 50% were A1A2 and 35% were A2A2. And by the way, I generally recommend, especially in this phase where we're not coding yet, that you just take a pen and paper and sort of follow me and do the calculations. They do seem trivial, and admittedly they are quite simple, but it's helpful, I think, if you just walk with me through these through this entire thought process here. So we then also established that we had that meant that we had 40% A1 alleles in the population and 60% A2 alleles. Okay, so these are the genotype frequencies, and these were the allele frequencies. And we were, of course, really interested in the allele frequencies because we initially defined evolution as the change of allele frequencies in a population over time. And so we need to know what the allele frequencies are. And just to recap, these are diploid individuals. So the reason why we have 40% A1 is because the full 15% of the A1A1 goes into is an A1 allele, and half of those, 25%, is an A1 allele, giving a total of 40% A1 allele. The same with the A2 allele, 50%, half of it is A2 from the heterozygote here, and the homozygote A2 provide the full 35%, so 35% plus 25% is 60%. Okay, so what next? So this is what we observed in the population. So now we would like to say, okay, what is the genotype frequency distribution and the allele frequency distribution in the next generation? And we can do this with Hardy-Weinberg. And I should say, Hardy-Weinberg actually makes a couple of assumptions. So one of the crucial things that I've actually just done here is to completely ditch individual counts. I'm just now using frequencies. And I'm doing this because Hardy-Weinberg actually assumes an infinite population size. That makes the math a little easier. It also makes a couple of other assumptions. For example, it assumes that generations are non-overlapping, which means that as one generation is born, the old generation dies. So there's only ever one generation alive. It also makes the assumption that reproduction is sexual, and it really doesn't care about males or females, just assumes that individuals have both sexes, also to simplify things. And mating is completely random, almost like molecules bouncing into each other in a gas. And there are no other processes in force as well. So no mutation, no natural selection, no migration. So this is a very, very simplified world. And I hear you say, well, but I mean, that's a bit too simplified, perhaps. Clearly, that's not what the world looks like. And you would, of course, be absolutely right. But the counterpoint is that this is a model, and the point of a model, of a thought model, is to capture only the essence of an idea and sort of get rid of all the other complicating things of reality. And perhaps the best analogy that I can offer is that of a map. I mean, assume you're trying to navigate a drive from A to B or a hike. you will take a map with you, and that map will be on a scale of, I don't know, 1 to 10,000 or 1 to 100,000. So practically everything will be missing from this map, but the map has the essential ingredients that allow you to navigate in the world. And you could, of course, have maps at increasing scales, at higher resolutions, and ultimately, if you would want to have the perfect map that really captures absolutely everything, you would have a 1-to-1 scale map. And of course, that map would be completely useless. So, as with maps, models sort of try to capture the essence of an idea, and thanks to that, they help you navigate the world in which you live in. And so, at the moment, we live in this very simplified world with all these assumptions, but it allows us to understand what is happening here. And then in future chapters and future lectures, we will be adding ingredients of reality like selection, like migration, like finite population sizes, and so on. But we will then have our null model that I referenced in one of the earlier lectures that allows you to understand what's going on. Okay, that's an important thing from a philosophical point of view, but it's really important to understand. Otherwise, you'll always be confused about models that make these simplifying assumptions. Okay, back to the math. So this is our status quo. This is what we have here. So now we could calculate, okay, what are the new genotype frequencies based on that? And so this is actually fairly easy to calculate. So once again, keep in mind, we have the A1 allele has a 40% frequency, and the A2 allele has a 60% frequency. Now we have infinitely many individuals, which means we have infinitely many alleles. And these individuals produce infinitely many gametes. And so you can sort of imagining generating the next generation by picking random alleles from this infinitely sized gamete pool. And for each individual that you want to create, you have to pick 2, right? Because we're diploid individuals. So what is the chance that you create an A1A1 genotype? Well, to do that, you have to first pick an A1 allele, which will happen with probability 40%, because that is the frequency of the allele. And then you have to pick an A1 allele again. That's again 40%. So the combined probability is 0.16. So there's a 16% chance that you pick 2 A1 alleles to create this diploid A1 genotype. What about A1, A2? Well, let's first go to A2, because that's a little easier. The probability to generate an A2 genotype is the probability of you picking an A2 allele, which is 60%, and picking an A2 allele again, which is also 60%. So the combined probability is 0.36. Now, all of these probabilities here will have to add up to 1 because they're mutually exclusive. You either generate an A1A1 or you generate an A1A2 or an A2A2. But one of these 3 things will happen, and so they all have to add up to 1. And so because you already know those 2 probabilities, you would actually already know the probability here, which would be 1 minus 0.36 minus 0.16, which would be 0.48. But let's make this explicit. So there are 2 ways for you to generate an A1A2 genotype. Either you could first pick an A1 allele, chance 0.4, and then an A2 allele, chance 0.6. So the combined probability here, 0.24. Or you could do it in the other order. So you would first pick an A2, and then you would pick an A1. And of course, again, the combined probability here is 0.24. So in total, it's 0.48. And now 0.86 plus 0.48 plus 0.36 gives 1. Adds up to 1. So those are the new genotype frequencies then. So the genotype frequency of A1 A1 is going to be 16% in the next generation. And of A1, A2, it's going to be 48%. And of A2, A2, it's going to be 36%. And compare that to what we had above before we got started. These were the genotype frequencies, 15, 50, and 35. So before we had 15, we had 50 here and 35. So you can see the genotype frequencies changed a little bit. This one has gone up by 1%. This one has been reduced by 2%, and this one has also gone up by 1%. So a change in genotype frequencies here. All right, so now it's getting really interesting. So now we have these new genotype frequencies in the next generation. So let's go ahead now and calculate the new allele frequencies, because again, keep in mind, evolution is a change in allele frequencies. So what are the new allele frequencies? All right, so we have A1A1 at 16% and A1A2 at 48% and A2A2 at 36%. Okay, so these guys obviously will contribute the full 16% to A1 because they're all A1. A1, A2 will only contribute half of half of their alleles, which is 24% to A1, and half of it, which is also 24% to A2. And the A2A2 genotype will, of course, contribute the full 36% to the A2 allele. Okay, that gives us a total of 16 plus 24, 40%, and 24 plus 36, 60%. Okay, so in short, the allele frequencies are now for A1, 40%, and for A2, 60%. Hang on a second. Wasn't that what we just had? Yeah, that was what we just had. That's what we started with. Interesting. Okay, so the allele frequencies haven't changed. Okay, so the genotype frequencies have changed in one generation, but the allele frequencies haven't changed. All right, well, let's see what would happen in the next generation. So again, to produce an A1 genotype, you would have to pick an A1 allele and then a second A1 allele. Hang on. I have a deja vu here. I've just done exactly this. Of course, whenever we start with these allele frequencies, we get these genotype frequencies here. There's no other way. And that, in fact, is the Hardy-Weinberg principle. It says that given a certain frequency of alleles, you should be at Hardy-Weinberg frequencies, which are very easy to calculate. So these are Hardy-Weinberg genotype frequencies. And the allele frequencies never change. And with these allele frequencies, you should expect these genotype frequencies. And if you don't have them, you will get them within a single generation, and then those frequencies will stay there forever. So there are two really interesting things that are happening here in the Hardy-Weinberg world. And I just want to show that graphically. So Hardy-Weinberg is the following. It means that your genotype frequencies, if they're not at Hardy-Weinberg frequencies, just giving you here some sort of example. so this is generation 1 and so on. So this is time. The genotype frequencies will immediately, within one generation, go to Hardy-Weinberg frequencies. Okay, so these are the genotype frequencies. Genotype, oh, excuse me, genotype frequencies. Within one generation, you're at these genotype frequencies. Now, if you look at the allele frequencies, things are even simpler. They just remain constant at whatever frequencies they are to begin with. Okay, again, time. So that is the Hardy-Weinberg principle. The allele frequencies don't change. Why should they? And given constant allele frequencies, you will have a specific genotype frequency distribution that is given by this Hardy-Weinberg principle. And if your population is not there at the beginning, it will go there within a single generation. So basically, unless you have changing allele frequencies, you should really expect genotype frequencies to be at Hardy-Weinberg. And in fact, if you read many studies about evolution, ecology, just population genetical studies, where people look at allele frequencies in populations and genotype frequencies, they will usually test whether the allele frequencies and the genotype frequencies are in line with Hardy-Weinberg. And if they're not, they will usually try to explain why they think they're not at Hardy-Weinberg, because then one of the assumptions of the Hardy-Weinberg model must be violated. And therefore, there must be something interesting going on. So that is the null model of evolutionary genetics. It's called Hardy-Weinberg. It's fairly simple, and it's about time we put this in code. I'll see you in the next lecture.